Welcome all of you. I'm going to show you how to do calculation for conduction experiment. Okay, so I will do it step by step. So if you have data like this, you can see this is with time. Okay, and then we have T1 to T9. This is actual position. Okay, so what we have a cylinder. Okay, cylinder. We are hitting at this point. So we are heater is applied here, and we are measuring the temperature along the length of T, the cylinder T1 to T9. Okay, so T1 to T9 at different axial position x1, x2 up to x9. So when we switch on the heater, we are taking the temperature with all the temperature from T1 to T9 at 5 minutes, 6 minutes, 15 minutes, 20 minutes. This is just to see that how the steady state will be reached, how you are going to reach the steady state. So you can see T1 56 at 5 minutes, at 10 minutes it goes to 68, at 15 minutes it goes to 75, at 20 is 80.5 and 25 80. So they are close. So you can see these values are close. It means that they are reaching steady state. So this with time we are just trying to see that how the steady state will be built. For the calculation we will use the steady state profile. Okay, steady state means at different steady state means at 25 we assume that it reaches the steady state. Okay, similarly here this is the final one, 21. We will use this temperature profile. Okay, and look like here we have whatever we have is the steady state. Okay, that's the steady state. So in case you don't have it time with time, okay, it means that your data is for steady state. Okay, now what we can do if we have a time, you can plot temperature versus x. What is this? Temperature why it is like this. Okay, a minute. Okay. So y-axis is T1 to T9. Okay, and x-axis is distance. And, let me move this. X-axis is distance. So it is like 0.01, 0.02 meter. Okay, so this is the profile at t equal to 5. This is not steady state. We will add the next one. Okay, so this one, the second one at 10, and x is the same, x-axis, and axial distance. Okay, we can say t equal 10 minutes. Okay, the one before it was t equal 5 minutes. Okay, and then we can keep adding. Adding means the third one is this. x-axis the same, and this is t equal 15 minutes. Okay, keep adding. I have the fourth one at 20, x-axis the same, t equal 20. Okay, and then one more, right? 25 at t equal 25 minutes. Okay, so what we see here, this is the temperature profile along the length of cylinder. So this, and you can show the legend. Okay, so now you can see t equal to 5 is this one, t10 is this one. So there's big difference, yes, because we switch it on the heater. Now T15 is okay, also big difference, but you can see the difference between 20 and 25 is very little. Okay, maybe next time if you take data after 5 minutes, both will be the same. So what we can say that uh, after 20 minutes it is reaching a steady state. So after 25 it is almost a steady state. There is not much difference in temperature when the time is 20 and 25. Okay, and that's it. Temperature is decreasing along the length of cylinder because of the thermal resistance, right? We have thermal conductivity, x over Ka is the thermal resistance. So there is drop in the temperature away from the heat source because of thermal resistance. This is one graph you can have. Okay, apart from now, what you do, just do it for one. Then what you need to draw only for steady state. Okay, so this is one steady state, and another one is this steady state, and then we have this. So we can plot only this one. Okay, plot as scattered data point again. Okay, let me move this, and then okay, add. So this is the steady state profile. X value is this. This is at 1 Q. So Q is here 31. So 31. Okay. So this is Q at 31. Now look at this data point 31, 31, 32. This is what? This is just fluctuation of the machine. This is the raw data from the student. So they noted as it is. So this is just fluctuation. What you can do 31, 31, 31. So you can make it all same. This is the same. Should not change. Okay. So this one, this profile is Q equal 31. Okay, and then this is steady state. What we need to find the slope of this. So temperature linear, right? dt dx we need. So the slope t versus x, that this is the profile of t versus temperature versus x. The slope will be dt dx, right? So dt dx in this case is minus 494.83. Got it? This is access title. If you want, I don't want to make the video very long. T, then this is x, right? The slope will be dt dx. So this is the dt dx. The slope minus 494.83. So what we need, we can plot the same for, sorry, and so now here we will take again steady state one, this one. X axis the same, and this is q equal how much? 20, 22. Okay, so you can see this is 22, 22, 21. So maybe I can, we can make it 22. So this is constant. So if you have a change here it means that that's only a fluctuation. So this one again we can add trend line, linear. The slope will be dt dx. So we have third data point, a second data point. We have one more. Select data, and this one no time, only we have. So this is steady state. X the same, and Q equal 13 watt. So now we can see this is the second one. And third one I can get the data point. Okay, so we have 3 dtdx for, okay, so if you have 3 dtdx you can find the k. So what we have, q dt dx, okay, dt dx, then you can find the k, right? Q is one is 13, and the next one is 13, 22 and 31, 22 and 31. Okay, and now the slope, the dt dx for 13 is minus 190. Okay, the second one is, this is the second one. Okay, minus 354.67. So this, you can see that this is decreasing. So slope is negative, right? The gradient is negative. And then 494.83. What is k now? Applying the Fourier law, q is minus ka dt dx, right? So k will be q over a dt dx. Area of the cylinder is 25 mm. So you can find the area. So area of the cylinder will be 3.5 times 25, 0.25 meter square over 4. So K will be Q divided by area. Area we can fix it, so you can use dollar sign, area divided by dt dx. Okay, minus sign I forgot, right? So minus is there, isn't it? It's minus. So now you can see what I got, 139.456. So again I am giving you the comment that you should use the significant digit. So 139.4569 doesn't make sense. So number maybe up to 1 digit. Okay. So this is the k value using axial conduction. So you have three values here. Okay, is this fine? So slope dt so this is from axial. Now radial. Radial you need to understand. So now see here, this is the data again with time. Again with time, this is the radial position. So radial conduction, how it is happening. So if you look at the front view, it is like this. This is inner cylinder. We are heating this cylinder, applying the heat here, and then we have outer cylinder. Okay, so outer cylinder, the inner radius is around, if you look at, I think 0.055 Ri. So it is here, and then we are measuring the temperature at these radial positions. Okay, so this is the R changing here. Okay, so now this, the temperature we are measuring here, that the first one is the Ti, the outer one is the To. Since we are heating at inner cylinder, so you can see the data. The first temperature is high, then there is drop in temperature. Again, due to thermal resistance. So what you can do again, you can plot this. If you want, I can do it again, repeat it. So if you can plot this one, okay, with train with R. This is the radial position. Okay, this time t equal 5 minutes. Okay, keep adding. This is t equal 10 minutes. And 15. T equal 20. Uh, Wait a minute, what happened? X is missing here. Okay, so the first one was t equal 5 minutes. So now you can see the same thing here. You can see if you add, show the legends. So same thing with time, this one and this one, and so after some time it is reaching steady state. I think I have missed some data point. Okay, so this one first, the second one, is 20. Okay, so you can plot all of them, and then you can see that you can say that with time state profile is building, and with that like profile for 20 minute and 25 minute, they are the same, so it is steady state. So it is reaching the steady state, so we'll use this data point for the steady state. This is the last one, is the steady state. Okay, this is just to discuss the how steady state is being formed. Okay, so now the next thing is how to calculate. So we will plot a steady state profile, uh, again 30, 31, 32. So this is around like 31, so make it 1, 31. Okay, so we'll use this profile steady state to plot. This is steady state profile along the radial direction. So position here is the radial. Steady state so this is along the length. Now what profile we should fit in for the axial conduction, we use linear. But if you look at the equation, okay, equation, this is the equation. So t versus r, this is logarithm, right? T versus r. So what you do, you fit a logarithm profile, logarithm. Okay, because the equation is logarithm, we can't force. So this is by the equation, by theory. Okay, now if you look at the requirement for the port using, okay, this one, calculate by using equation 4, this one. Okay, equation 4, what is equation 4? This one. So ln ro outer divided by inner, t outer, t inner. Okay, so q, for example, this one q is 31, right? So this is the q is 31. So k will be q 31 times ln ro, the outer radius. So outer radius is, if you look, see here, outer diameter is outside diameter 0.110. So this outer diameter is 0.110. So this is the diameter, so divided by 2. Okay, or you can do the r o r I. Okay, r I. So ro is 0.110, okay, divided by 2, and then this one is 0.012 divided by 2. Okay, so k is, I'm applying this equation, k is q times ln roo divided by ri. Okay, this is one divided by 2 pi 3.14 times the length. Length is the thickness basically. So that's given, right? 0.004. 0.004. What else? I think that's it, right? Okay. 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 Temperature difference. So then what we have times temperature difference. So outer is the uh, small inner is this T1 and outer is a T6. Okay, 1 minute. Just wait. Okay, so this is 2 pi lk times outer is this T6. Okay, To minus T, outer is T6 minus Ti, inner is the T1. Okay, I think that's it. So it gives you minus. Is minus means that it has already minus. So I missed the minus here. This is minus here. So the equation I should use minus. So now I got 122. So if you have more than one data, you can do for different value of Q. Okay. So what I got here, you can see this is from radial. I can add this one from this is axial, right? So this one I got it 122, 122. So 122 from radial. Okay. Okay. This is one way. One more way it is like this. What is asking? Plot ln r versus t. Okay. What is that? So ln r versus t. So we linearize this equation. So if you look at this top Q, so ln RO. So RO is the outer diameter. Okay, from here, this is inner, and then we have outer here. So outer is varying. Okay, so RO we can make it like R, changing. So Q ln R minus Q ln Ri equal 2 pi L K T naught minus 2 pi L K T I. So T naught, the outer temperature, this is changing. So this is basically, we can make it variable. So this is T. So what we are doing, we are plotting ln R versus T. Okay, ln R versus T. So slope will be 2 pi ln K over Q. That's the slope of a straight line we are going to get. Okay, so this is Y and this is X. Okay, please. So 2 pi lk over q, that will be the slope. Now come to this. So what we are going to do, this is R. So ln R we can calculate. Ln R. So just drag this one. So ln R, then plot ln R. Okay, we want this one. Ln R versus the temperature. The temperature is this. You can say ln R versus T. Okay, so this one, the third point, last data point is not coming very good. So it's okay. We can draw fitted linear trend line linear. Then you can see r square is still okay, close to 0.9. So in this case, slope is this graph slope is minus 0.0868, right? So this is the slope. So in this case, this the slope is this. So 2 pi L K over Q equal to the slope. So what we need? We need K, right? K will be Q times slope over 2 pi L. L is the length. Length means basically the thickness. So now Q times slope. So K will be K. Q is 31, right? 31 watt times slope divided by 2 pi L. L is 0.004, right? So Q times 2 pi Lk. So K is Q times slope 2 pi Lk. Yes. And again, slope will be negative, isn't it? So again, oh, this is negative. So in this case, we got K 107. Again, no need like too many data point digit. So 107.1. So this one is little bit far. Then this is 122 and this is 107. Okay. So K value should be same, right? So this changing little bit depending on the data accuracy. So you can find the K average. So 124.5, which is very close to the value given, isn't it? And then you want to see the deviation, a standard deviation, like K is supposed to be same, but is varying, yes, because this is experiment. So deviation is around 11. Deviation, standard deviation. So again, maybe no data point, no decimal, 12. So you can say that my K value is 124.5 plus minus 12, plus minus, okay. So there is a deviation. Maybe some of you will get better result, okay. So this plus minus. So 124, the K equal experimental 124.5 plus minus 12. Okay, you can see that deviation is small or big. It's still small, not very big. Okay, so this concludes all the calculations. So I hope it will help all of you. Thank you very much.